You don't say. Okay, let's go ahead and begin. Okay, we're gonna do talk about 9.3 today. Oops. Hypothesis tests. okay, and their errors. So what does it mean to be wrong when we do a hypothesis test? Okay, well, there's two types of errors, okay, type 1 error and type 2 error. Okay, type 1 is when you reject the null, but it's actually true, okay? So the way that I think about a type 1 error is I think about, okay, the fact that I've created these areas of rejection. Okay, type 1 error, I've created these areas of rejection, but the area of rejection was too conservative. I included too much in it, and I accidentally you know, said that this was false. Okay, let's say that we're over here. Okay, I said that the null was false when it actually was true. Okay, that's the type 1 error. Okay, is you reject the null when it's actually true. Okay, so you falsely rejected it. Okay, the other type of error that we can have is that, am I recording? Make sure that I'm recording.
You are recording.
Okay, thank you. Okay, good. Okay, the other type of error is that we fail to reject. Oops. Let me get this stuff over. There we go. Okay, is that we fail to reject, okay, the null when it actually is false. Okay, this one is actually false. Okay, the null was actually false. So we failed to reject, which means that we actually were here in our value, and our area of rejection was just not large enough. It was too small. Okay, and so okay, we failed to reject because we were not in the area of rejection, and therefore we failed to reject. So those are some errors. We're not always going to be correct, right? Sometimes we're going to falsely reject, okay, and sometimes we're going to fail to reject. Okay, this isn't foolproof. Okay, so we're only, if we have a 5% region of rejection, then we're only 95% certain that we guessed correctly. Okay, example 1, write the null and alternative hypotheses, and identify the type 1 and type 2 error in context. Okay, okay, 10% of all people writing with their left hand. Okay, so what is the null? Okay, the null would be that the proportion of people writing with their left hand is 10%. Okay, what would be the alternative? The alternative would be that it's not 10%. Okay, so we would conclude, okay, for a type 1 error, we would falsely reject the null. We would actually reject when we shouldn't have. Okay, it was actually true that this 0.10 was correct. Okay, this was actually correct, but rejected. Okay, so down here, I'm just going to say we're going to conclude, we would conclude that the proportion was not 10% when really it is 10%. Okay, so that's type 1 error. For me, type 1 error is the easiest one to remember. If I can remember type 1, then I just know that type 2 is the opposite. But type 1 is easiest to remember, and it's kind of like a little tongue-in-cheek And how I remember that, it's just I always reject my hose. Okay, so I always reject my hose, and that's a type 1 error. If you're always rejecting your hose, then that leads you to a type 1 error, because you would falsely reject hose that don't need to be rejected. Okay, maybe they're a good hoe. Okay, I don't know. Okay, but type 1, I always reject my hose, and therefore I'm going to end up with type 1 errors if I'm constantly rejecting them. Okay, and maybe they don't need to be rejected. Okay, what about a type 2 error? Type 2 error, okay, my null hypothesis is, okay, probability is 10%. My alternative, again, probability is not 10%, and this is for left-handed people. Okay, I would conclude that the proportion, I could put it, of their left-handed people is not 10%, when really it is. Okay, that would be for type 1. For type 2, what would we do? We would falsely not reject, right? We would conclude that the proportion of left-hand people is 10% when really it is not. Here we accept our null hypothesis when it really should have been false. Okay, so it's kind of what we call the converse statement of the type 1. Okay. Okay, let's see how this works out with us. Okay, it says write the null and alternative hypotheses. Okay, identify the type 1 and type 2 error in the context. So let's do another one of these. A hardware manufacturer needs to keep the defect rate of 0.01 or less. Okay. Okay. In order for their shipment to be approved. Okay. A sample was taken from every shipment, and a shipment is approved unless there is evidence that the defect rate is significantly higher than 0.1. Okay, so it's rejected unless it's it's approved unless it's higher than 0.01. Okay, a sample of a certain product found.
You're really breaking up. We can only hear like one of every third word.
Well, okay. Let me see if I can change my connection. Okay, let's start example 2 over. Let me get rid of this thing. There we go. Okay, write the null and alternative hypotheses and identify the type 1 and type 2 error in context. Okay, a hardware manufacturer needs to keep the defect rate at 0.01 or less in order for their shipment to be approved. A sample is taken from every shipment, and the shipment is approved unless there is evidence that the defect rate is significantly higher than 0.01. Okay, a sample of a certain product is found found a defect rate of 0.017. So that's what I would be testing against. Okay, so we need a defect rate of less than 0.01. Okay, so we're going to make the the null to be p equals 0.01. We'd like this to be less than 0.01. Okay. Right? Or no, higher, sorry. We're going to reject it unless we're higher than 0.01. Okay, higher than 0.01. So let's go with that one. Okay, type 1 error here. Type 1 error, we reject the hoe. Okay, we reject the null. So we would conclude, okay, that the proportion is higher than 0.01 or 1%, when really it is 0.01 or lower. Okay, we reject when we shouldn't have. Okay, we reject parts that could have been sold, okay, when we shouldn't have rejected them. We were too conservative. Okay, this is too conservative. We're rejecting stuff that doesn't need to be rejected. Okay, these are defective parts, right? Too conservative. Okay, what about type 2 error? Type 2 error is that we accept the alternative when we shouldn't. So we would say that the proportion of defective parts is greater than 0.01. Okay. Okay, when really, okay, no, we're accepting the null, is 0.01, I should say, is 0.01 or lower, when really it is higher than 0.01, okay, and this is, okay, not conservative enough. We're letting stuff through that shouldn't get through, okay, not conservative enough. Now, which is worse for the consumer? Okay, we got to think about the producer. For the producer, okay, for the producer, type 2 is better because we're actually selling stuff that, okay, we shouldn't sell. For the, or sorry, for the, okay, so type 1, we're accepting that it's 0.01 when it shouldn't be. Okay, that's type 1. Okay, so we're letting stuff through that shouldn't go through. Okay, or sorry, we're not letting stuff through for type 1. Okay, we're being too conservative here. We're not letting stuff through. That's better for the consumer because they're not going to get bad stuff. Okay, we're being too restrictive. So think of type 1 again. I'll draw a diagram here. Think of type 1 as just having really big tails. Huge tails here. And we're saying that we're going to reject everything except for this little strip in the middle. Okay, we're too conservative on our tails, on our rejection region. We're rejecting everything, right? So that's better for the consumer. If we reject, they're only going to get, think of it like fruit, right? Fruit with blemishes, right? So all the blemished fruit is on the tails here, really bad fruit. Okay, maybe it just has a few blemishes. Okay, that's not going to get sold. Only the pristine fruit is in the middle here. The stuff that's really, really, you know, looks like it came out of a magazine. Okay, that's the stuff that's in the middle. Okay, so this is really conservative. Okay, now that's better for the consumer. What's worse for the consumer? Well, what's worse for the consumer is type 2 error. Okay, because why? because our tails are so tiny that we're doing what? That we're letting everything through. We're letting stuff that has blemishes through. We're letting stuff that is a little moldy through. And we're just saying, oh, it's okay. We're going to sell that anyway. And we're letting everything through that shouldn't come through. So what's worse for the consumer? That's type 2 error. The type 2 error is we're letting stuff through that shouldn't have gone through. Okay, so type 2 error is worse for the consumer. Okay, more defects are going to get through. Okay, example 3 says a school claims that 40% of its seniors are attending a UC or Cal State next year. Okay, 40%. John thinks this estimate may be wrong. Okay, write hypotheses John should use to test this claim. Explain what a type 1 error is in this context. Okay, so the null hypothesis is that this is correct. The probability of people going to a four-year university outside of private schools is 40%. Okay, he thinks that this is wrong. Well, it doesn't tell me if he thinks it's too high or too low. He just says that it's wrong. You, sir, are wrong. Okay. Okay, so what's a type 1 error in this case? Again, type 1 error is rejecting way too much, right? Rejecting way too much. So what's a type 1 error? Type 1 error is concluding, okay, we would reject the null and we would accept the alternative. We reject our HO, okay, our HO, okay. Type 1 error is concluding that the probability is not equal to 40% when it actually is. Okay, that's type 1 error. Okay, type 2 error would be the opposite. Okay. Okay, power of a test. This is the probability of correctly rejecting a false null hypothesis. This is, okay, the probability of getting it right, that we correctly reject it. Okay, that we don't have a type 1 error. This is the probability of a type 1 error, okay, which is the complement of a type 2 error. The two are opposite of each other. Okay. Okay, so this is the probability of not getting a type 1 error. The power of a test depends on the true value of a parameter, which is often unknown. But the more powerful our test, the better. In order to increase the power of a test, we wish to make it easier. So this is 1 minus, okay, the complement, so the power of the test, okay, the probability of correctly rejecting, okay, the probability of not getting a type 1 error is 1 minus the probability of getting a type 2 error. Okay, so that's your formula. Okay. Okay, probability of not getting type 1 is equal to 1 minus the probability of type 2. Okay, so think of this as, well, what's the probability of getting a type 2 error? Probability of getting, we'll say that that's 30%. Probability of type 2, okay. Oops. How do I spell type? There we go. Type 2 is 30%. You got a 30% chance of falsely accepting the null, okay? So failing to reject failing to reject the null. Okay, so then what would be the probability of not getting a type 1? Well, it's 1 minus probability of getting a type 2, okay? And so that is 1 minus 0.3, which is 0.7. You have a 70% chance of not getting a type 1. Okay. So in order to increase the power of a test, we wish to make it easier to reject the null. Okay, so what would make it easier to reject the null? Let's draw a picture of this. Okay. Again, easier to reject the null means that we want really large tails, right? Easier to reject means that we want really large tails, Okay, easier rejection. Okay, so what's going to create really large tails? Well, okay. One thing that we can do is we could increase the significance level. Okay, what does increasing the significance level do? Well, say that we go from alpha of 0.05 to alpha of 0.15. What does that mean? Well, it means that, say I have these values, okay, and I know that what the standard deviations are, okay, and I know that this is the middle, right? And so maybe it looks like this, okay, from my graph. And so alpha being 0.5 is going to be 2 standard deviations away from the mean. But what is alpha of 0.15 going to look like? If we do alpha equaling 0.15, what's that going to do to my tails? Well, it's going to bring them in. It's going to bring those tails in significantly. So we could increase the significance level. That would make it easier to reject the null. Okay, that would make it easier for a type 1 error to occur. Okay. Okay, so what about number 2? Okay, what else is going to make it easier or give me bigger tails here? Okay, well, let's compare 2 different graphs. Let's compare one that's really wide, okay, to one that's really narrow. Okay, so let's say that in the really wide one, okay, I have, oops, I don't like the way that's drawn. Sorry, let me draw it again. Okay, so again, we have really wide. Okay. We have our middle, our mean. Okay, say that we have 1 standard deviation and 2 standard deviations. Okay, 1 standard deviation and 2 standard deviations. Okay. Okay. And so this guy, right, is one graph. Let's talk about this guy compared to the other graph, which is going to look like this. Okay, come down like so. Okay. Now, where this would be maybe 1 standard deviation, and this is 2 standard deviations now. This is 1 standard deviation and 2 standard deviations. Okay, so which one's going to get me wider tails? Okay, think about my sample size. Sample size. If my sample size is small, or my sample size is big, right? Sample size is big, small, sample size is big. Which one of these is going to correspond to small sample size, and which one's going to correspond to big sample size? So let's start with the red one first. So for the red one, the sample size is small. Okay. Okay, so if the sample size is small, right? The sample size is small, then if I choose a certain value here, if I choose a certain value to cut off from my small sample size, I get really big tails. Okay, I get really big tails. But, okay, if my sample size is large, then I get really small tails. That's these guys right here. For the same values, for the same cutoff, I get really small. So which one's going to give me more area of rejection? Which one's going to give me more area of rejection? Well, yeah, it's the small sample size. That's going to give me a bigger area of rejection based on the same alpha. Okay, bigger area of rejection based on the same alpha. Okay, so a small sample size there. Okay. Okay, so that's the end for 9.3. Let's jump into chapter 10 now. Okay, 10.1. Okay, so here we're going to do two proportion z-test, two proportions. Today I'm going to just focus on the proportion part. On Thursday, we're going to finish this up, going over the mean part. Okay, I'm only going to do proportions today, and then we're going to do means on Thursday. Okay, so means, and then we're going to do some practice problems. Okay. Okay, so we're going to perform a 2-sample proportion test. So this is 428, and then 2-sample t-test, that's going to be 430. Okay, we're going to interpret the p-value in context and comparing it to its alpha value. Okay, we're going to interpret the confidence interval, okay, as a hypothesis test. Okay, interesting. And we're going to interpret StatCrunch output for 2 proportion tests. So I might do it on the calculator as well. I will definitely be using StatCrunch. Okay, so the first one is for proportions. Let's talk about proportions today. Okay, we want a 2-proportion z interval, okay, or a 2-proportion z test. Okay, when are we going to use the proportion z interval, and when are we going to use the proportion z test? Okay, we use a z interval when we're guessing how much. Okay, we use an interval when we're guessing how much. We're trying to guess something about the proportion, and we're trying to close in on that interval. Okay, guessing how much. Okay, the 2-proportion z test is a hypothesis test, and we're going to, here we're not guessing how much, we're saying, is the value given true? Is the value given true? Different questions. Here we're guessing how much, and for the intervals and the z-test, we're asking, is the value true? Okay, is the value true? Okay, so some example questions that we're going to be going over. Okay, are men more likely than women to drink black coffee? Men more likely than women to drink black coffee. Okay, is that a guess of how much or how much more men drink black coffee? No, it's not how much more. So is it an interval or is it a test? It's a test. Okay, this is a test. Okay. What about this one? How much more, oh, look at that. How much more do Democrats support the Affordable Care Act compared to Republicans? How much more? We're looking for a value, and therefore that is an interval. That's an interval. Okay, what about, is the proportion of 35 to 45-year-old drivers that have been in an accident within the past year lower than the proportion of 16 to 25-year-old drivers that have been in an accident? Is it asking me how much? No, it's asking me, is it lower? It's a comparison between the two. We're just going to compare the two populations, the 36 to 45s and the 16 to 25s. Okay, is it lower? Is it lower? That's going to be a test. Okay, okay, two sample t intervals. We'll get to means a little bit later. Okay, we'll come back to this on Monday, or sorry, on Thursday. Okay, how do we compare two values? How do we compare two values? We look at the difference. Okay, we look at the difference of the values. We look at P1 minus P2. Okay, that's how we do. We find the difference in the values. Okay, how do we find the standard deviation of the difference? Well, here's the formula for standard deviation. You by no means do not need to memorize this. We're going to use technology to get this. Okay, you just be aware that it exists. Okay, awesome, wonderful that you're aware of it. You don't need to memorize it. Okay, we're going to use technology to get that. Okay, that's the standard deviation of the difference, Okay, how do we compare two things when there's a difference, right? How would you compare two things if there's by the difference? Well, if I want to know that P1 is equal to P2, what would the difference be? What would the difference be if the two were equal? When I subtracted the two, P1 minus P2, wouldn't that be equal to 0? If they were equal, say it's 3 is equal to 3 or 0.3 is equal to 0.3, the proportions in the two populations are the same. Well, wouldn't the difference be 0? Yeah, it would be 0. What if P1 happened to be bigger than P2? Say that P1 is, say, 0.5 and P2 is 0.3. What happens when I subtract them? What happens if I subtract a big number from a small number? Well, it's a positive number, right? So big number minus small number is positive number. Okay, this is where we care about the sign. So wouldn't that be greater than 0? Right? Wouldn't the difference be positive? Yeah. And the opposite would be if P1 is less than P2. For example, if 0.3 minus 0.5, that would be negative 0.2. And so that's a negative answer. So P1 minus P2 is less than 0. What does it mean to be less than 0? Well, it means to be negative. It means to be negative. Okay, we're going to skip that. Okay, let's try example 1 here. Example 1. Okay, 48% of 500 students randomly sampled from college A. Okay, so they're going to give us a lot of information. We're going to want to write down the information they give us and try to organize it. Okay, we're going to want to organize the information before we like read these, and then we're like, what did I just read? I'm totally lost. Okay, let's organize. So for college A, it has 500 students. Were randomly sampled. Okay, so that is n is equal to 500. Okay, and maybe I'll do a little n sub a for knowing that it came from college A. The proportion of the sample, this is not p. This is p hat of college A, because it's the sample proportion. It's the sample proportion is 0.48. 0.48. Okay, that's the sample proportion. Okay. Okay, what about college B? College B. Okay, well, we want, it says that 67% of the 625 students from college B. So NB is going to be equal to, okay, 625. And P hat B, this is my sample proportion of B, is 0.67. I want to know, is there a significant difference? Is the difference between the colleges significant in order for me to say that they are not equal? Okay, they are not equal. Okay, so 48% of 500 drive to school. Got to say, okay, what are they asking us? They're saying that they drive to school. Okay, they commute to school. And then of the other college, 67% of college B, okay, drive to school. Okay, college B drive to school. Estimate how much more. Estimate how much more of a proportion of the students from college B drive to school compared to the proportion of students from college A. Okay, so what are we asking here? Well, we want to find an interval because it's asking how much more. We want to find a value, okay, a comparative value. So this is a 2 prop Z interval. It's a 2 proportion Z interval. Okay, why? Because it's asking me how much more. Okay, it's asking me for a value. Okay, it wants, you know, something concrete, a concrete number to give me an idea of how much more is B compared to A. Okay, so how much more is B compared to A? Okay, number 2. Well, what's going to be the difference that I want to look for? Well, it's the proportion of college A, or sorry, college B. Okay, college B minus the proportion of college A. Right, and I want to see, is this thing going to be positive? Is it going to be equal, or is it going to be 0? Okay. Okay.
Professor, just curious, why is college B your P1?
Because it says, estimate how much more of a proportion of college students from college B drive to school compared to the proportion of students from college A.
Okay, thank
So
you.
I just went in order there. They compare B to A.
Okay.
Okay. So we want the difference in the proportions. Okay. And is it a significant difference? Okay, so I want to see, are these, you know, can I even do this? Can I run the numbers? Are the criteria met? Okay, are the samples independent? Sure. Are they random? Sure. And then are both of these greater than 10, okay, for the sample sizes? Is NA times PA greater than, okay, or I should say P hat A, because we don't have P, we just have P hat. Okay, P hat is that greater than equal to 10? Okay, is NA times Q hat A greater than or equal to 10? Okay, is NB times P hat B greater than or equal to 10? And is NB times Q hat B greater than or equal to 10? Okay, so I'm just going to multiply 0.48 times 500. Okay, 0.48 times 500, and I get 240, which is greater than 10, so that checks. Here, Q is going to be 0.52 times N, which is 500, NA, which is 500, and that's going to be 260, which is greater than 10, so that checks. Okay, that's a 0.52. Okay, what about the proportion for college B? That's 0.67 times 625, which is equal to 41, we'll call it 419, we'll round, which is greater than 10. We just need to know what the ballpark is because, 419 is much bigger than 10. And then this is 0.33 times 625, which is about 206, which is greater than or equal to 10. So that checks. They all check. Okay, so all of our criteria hold. Okay, so now let's actually run the numbers. Okay, let's run the numbers here. Okay, so we want to know, let's do an interval. Let's first do this on the calculator, and then we'll do it on StatCrunch. Okay, in order to do it on the calculator, we need to go to, stat, and we're going to go to tests. Okay, and we're going to look for that 2prop z int. 2prop z, it's two proportions this time. Okay, and we don't want the test, we want the interval. Okay, we want the interval. So 2prop z int. So it's looking like that's number or letter B here. So 2prop z int. So it's under stat. Okay, let me move this over. Okay, stat, and then tests, and then B, letter B. Okay, for 2prop z int. Okay, I'm going to hit enter on that, and it's going to say, well, what's your X1? How many people in college B, okay, in college, or sorry, how many people in college, yeah, because X1 is B, sorry. Okay, so this is P1 minus P2. Okay, so X1 is college B. So in college B, how many people, okay, were drive to school? So I'm going to put that in as my 419 that I got here. Okay, 419. Okay, out of a total of 625 for college B. X2, okay, is going to be how many people are at 48%? That's 240. That's X. Those are my number of successes. People that drive to school in college A, and then this is going to be 500. Okay, and then we want a confidence level. They don't give us the confidence level, so we're just going to keep it at 0.95. Okay, so use 0.95 confidence level. Okay, so we're going to hit calculate. Oops, and it says that I have a domain error. Okay, why is that? Why do I have a domain error? Let's see. Let's go back here. I must have put something in wrong. Okay, so, oh, N, I didn't put in N properly. 625, right? Boom. Now hit enter, 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 enter. Oh, this one's in wrong too. 500 for that one, enter, enter, enter. Okay, so this tells me that I have 0.13317 to 0.24763. Okay, so what's my conclusion here? My conclusion, because this is a confidence interval, is that I am 95% certain that the difference in PB minus PA, the proportions, the difference in the proportions of college B minus college A is between 0.13317 and 0.29763, okay, which tells me what? It tells me that the difference had to have been positive. Why? The difference had to have been positive because these numbers in my confidence interval only contain positive numbers. Okay, these are all positive values. Okay, they're all positive values. No negative values, and not even zero. Zero isn't even included there. If zero was included, then I could say, oh, it could possibly be equal. If it was negative values, then I would say, no, it's less, B is less than A. But because it's positive, what can I conclude? Okay, I can conclude, which means that college B has more drivers than college A. Okay, that's what that means. It means that it has more drivers because, again, probability of B minus the probability of A must have been greater than zero. It must have been greater than zero, which means that the probability of B is greater than the the proportion of B was greater than the proportion of A, which is kind of easy to see. It's easy to see that, you know, yeah, we have 48% of 500. That's a really large sample size. So that 48% is probably pretty accurate. And then at college A, and then at college B, we have 67% of 625. So what would you say? Yeah, 67% is probably going to beat out the 48%. And because we have such a large sample size, these, if we were to kind of graph these, right? If we were to graph these different colleges, they might look something like this. A sample size of 500 is going to make an extremely narrow graph. The larger the sample size, the less variation my graph has. So maybe it looks like this, right? Where the mean, okay, would be at 48%, 0.48. That's college A. Okay, whereas here, I would have college B be at 67%, right? And so you get not even an overlap to where they could possibly be equal to each other in the same you know, population. I can't have the population of college A. There's very little overlap. There's a little tiny bit of overlap, very little overlap in, you know, kind of our hypothetical graphs here, but it doesn't even reach 0.48 for college B. College B doesn't even include 0.48, and college A doesn't include 0.67. So if I took 0.67 and I subtract off 0.48, I would get a positive result, which is what this confidence interval tells me. It tells me that I'm getting a positive result. Okay. Okay, and that tells me that college B has more drivers on average than college A. That's my conclusion. So the confidence interval helps me conclude something about the statistics. Okay. Okay, we're going to skip example 2. Okay, and we're gonna jump into example 3 here. Okay, we'll come back to example 2 on Thursday. Okay, example 3. Writing hypotheses for a hypothesis test. Okay, writing hypotheses. So we're just going to write the hypotheses, and then we're going to do one example for the hypotheses, and then we're gonna call it a day on the lecture here. Okay, so let's write the hypotheses here. 42 men and 54 women were randomly selected and asked if they prefer vanilla or chocolate. 27 men said they prefer vanilla, and 28 women said they prefer vanilla. Is there a difference in the preference between the two genders? Okay. So what would be my null hypothesis? I'm just trying to compare the two. Well, there's a proportion here, right? Proportion. So is the proportion of men equal to the proportion of women who like vanilla? Okay. So the proportion of men liking vanilla, is that the same as the proportion of women liking vanilla? Okay. Okay, we could also write this as is P men minus P women equal to 0, meaning that there's no difference. There's no difference in the genders. That's what would be for my null hypothesis. My null hypothesis would say that there's no difference. No difference. Okay, what about my alternative hypothesis? What would be my alternative hypothesis? My alternative is that there is a difference. Now, does it tell me whether it's more or less? No, it just tells me that there's a difference. So the probability, or the proportion of men liking vanilla is not the same as the proportion of women liking vanilla. Okay, or we could say that PM minus PW is not equal to 0. Okay, so that there is a difference. Okay, a difference exists. Okay, so, and this would also be called a two-tailed test. This would be a two-tailed test, so keep that in mind when you're doing your significance levels. You're going to want to make sure that you're doing two tails. Okay, so you break you break up alpha into 2 pieces. If alpha is 0.005, you're going to break it up into 2 pieces there. Okay, or you're just going to plug it into you're just going to plug it into a calculator or a StatCrunch. Okay, let's go back to, real quick, let's go back to this guy here, example 1. I said I was going to do this in StatCrunch. I didn't do that. Let's do number 4 now. Okay, in StatCrunch, which is actually right here. Okay, so let's try doing it in StatCrunch. Okay, how would I get the confidence interval in StatCrunch? How would I get the confidence interval in StatCrunch? For 2 samples, 2 sample proportion. Okay, so we want to go to stat. And I want to go to summary stats, I believe. No, proportion stats. Sorry, proportions, right? And we want to go to two sample this time because we're talking about proportions. Okay, two sample, and then this is with summary, Okay, two samples this time. It says number of successes, that's X, okay? In our first one, okay, for our first college, that was college B, okay, college B had, I believe it was 419, oops, and the number of observations was 625. The number of successes in sample 2 was 240, I believe. Was it 240? Yeah, 240. And then this is 500 in sample 2. Okay, we want a confidence level of 0.95. Okay. And then I'm going to click compute on this. And it gives me, okay, my lower limit and my upper limit as the same thing that I got in the calculator. And it says, hey, those are positive, which means that it means that 1 proportion of population 1 was bigger than 2, which 1 in this case was B, because it came first in that last sentence. Okay, so that's just how you would do it in StatCrunch, just to let you know. Okay. Okay. So again, we're going to skip example 2. Now let's do we have the same thing here, but we're going to write a hypothesis test. Okay, hypothesis test. Okay. It says 48% of 500 students randomly sampled from college A drive to school. 67% of 625 students sampled from college B drive to school. Is the proportion of students at college B who drive more than 10% higher? So now they give us something to compare to. More than 10% higher. Okay, so that tells me that the probability of B minus the probability of A, okay, is more than 10%. That's what we're looking for. Okay, is B minus A bigger than 10%? Is the difference bigger than 10%? So what would HO be? Well, HO would be that they are equal, always equal. The null always has the equal sign. So the probability of B is equal to the probability of A. Okay. Well, what's the alternative? Well, the alternative, okay, is that the probability of B, okay, is greater than the probability of A. Okay, or, okay, the way that I could rewrite this is I could say that the probability of B minus the probability of A is equal to 10%. Okay. Okay. Because we want to include this 10%. Want to include that 10% if we can. Okay, and then the probability of B minus the probability of A is greater than 10%. Okay, greater than 10%. So that's how I write the hypothesis for these. Okay, it's more than 10% higher. Okay, is the difference more than 10%? Okay, let's do example 4 here. Okay, example 4. We'll go back to vanilla and chocolate here. Okay, so we want to write a hypothesis test for there. Is there a difference in the preference between the two genders? Is there a difference? Okay, so what do we get? we're going to have our null as that the proportion of men who like vanilla and the proportion of women who like vanilla is the same. Okay, same proportion liking vanilla. Okay. Okay, why are we talking about vanilla? Because that's what they give us stats on. They could say 27 men prefer vanilla. We could also talk about the chocolates, but we really don't care. Okay, we know that if this isn't true, okay, then we're either going to get less men liking vanilla, which means more women like chocolate, and vice versa. Okay. Okay, so what about the alternative? The alternative here is that the probability of men, okay, is not equal to the probability of women, that they're different, okay? That there's some sort of difference, okay? Okay, so how can we test this? What's the test that we're going to use? We're going to use a 2-sample proportion Z test. It's really long. Okay, 2-sample prop Z test, proportion Z test. Okay, 2-sample proportion to Z test. Okay. Okay, number 3. Let's test that, you know, the criteria works. So is it independent? Check. Is it random? Check. We're just going to assume those are true. Is n times the men times the proportion of men greater than or equal to 2? Okay. Or sorry, greater than or equal to 10. I don't know why I put 2. Okay. Well, that just equals x men. Okay. Not to be confused with the Marvel franchise. Okay. But the x for men is just the number of men who liked vanilla. Okay. And the number of men who liked vanilla was 27, and that is greater than or equal to 10. The number of men who did not like vanilla is just going to be 54 minus 27, which is the other half, right? So that's 27. So 27 is greater than or equal to 10, so that checks as well. Okay, this is n times nm times qm, okay, which is just the number of men who did not like vanilla. They like chocolate. Okay, looks like it's pretty much split 50-50. Okay. Okay, what about the X women? Okay, the X women, which is the N women times the probability of the women. Okay, this was equal to 28. 28 out of 54, right? So 28, which is greater than or equal to 10, so that checks. And then let's do the N women times Q hat women, which is just the number of women who did not like vanilla. So that would just be 58 minus 28, or sorry, 54 minus 28. Oh, you know what? I screwed up on the men, didn't I? The men is not 54. The men is 42. I did that wrong. There are 42 men. So 42 minus 27. Sorry about that. 42 minus 27 is 15. So this is 15, not 27. Okay, but that is still greater than or equal to 10, which is good. Okay, this is 28. Okay, this is going to be 54 minus 28. So 54, oops, not 50, 54 minus 28 is equal to 26, which is greater than 10. So that checks. Okay. Okay, now we're going to use the calculator or StatCrunch to run the numbers. Okay. So maybe we'll go back to StatCrunch real quick and do the hypothesis test this time. So we're going to go stat. Okay, stat proportion to sample with summary. This time we're going to compare men to women. So the number of people, the number of men who liked vanilla was 27, right? I believe. Where are we at? Yeah, 27 out of 42. So 27. Okay, out of 42. The number of women who liked it was 28, I believe, out of 54. Okay. Yep. 28 out of 54. Okay, and we want to know, is there a difference between the two, right? So we want to know, is there a difference? So hypothesis test for P1 minus P2, okay, that looks good. Okay, P1 minus P2 is equal to 0. That means that there's no difference. Okay, P1 minus P2 is not equal to, that's what we wrote. That means there is a difference. Okay, the difference is not equal to 0. There is a difference. Okay, and we just want to know what this is. So let's calculate the hypothesis test. Move this over so I can actually compute it. Okay, so I'm going to click compute. Okay, and it tells me that I get a p-value. Okay, I get a z-score. Let's go back to this. So I get a z-score of 1.22. Okay, I believe that's what this is. Yeah, a z-score of 1.22 and a p-value of 0.2218. Okay, so z-score of 1.22 and a p-value of 0.2218. Okay. So now on StatCrunch, it doesn't show the PM equaling PW. It shows PM minus PW equals 0. It's the same thing. And then this one, it doesn't show PM not equal to PW. It shows PM minus PW is not equal to 0. Okay, so now let me show you how you do this on the calculator, because the calculator uses the first ones here. Okay, so I'm going to go to stat, tests, okay, and I want two prop z test. Okay, two prop z test. Okay, which is number 6. Oops, I don't know why that did that. Okay, which is number 6, I believe. Okay, going to test my hypothesis test. Now we're going to go to 6, and it says, okay, how many successes in my first group? How many men like this? It was 27, I believe, out of 42. Okay, what was how many successes in my second group? That was 28 out of 54. And I want not equals. P1 is not equal to P2. And I want to calculate this. And it gives me the exact same z score and p-value. The p-value is 0.2218. Now, 0.2218 is greater than 0.05. If I use a significance level of 0.05, then what's my conclusion? Am I going to accept the null, or am I going to reject the null and accept the alternative? Well, I'm going to accept the null. Okay, or we say fail to reject the null. We don't know that he's true, but we're not going to say he's false. Okay? We're just not going to say it. We don't have enough evidence. So what does this tell me in terms of my scenario? Well, it tells me that there is no significant difference between the proportion of men and proportion of women liking vanilla. Boom. Okay. There's no difference. Okay. So the tastes were not dependent upon the gender. Okay, we're going to stop there for today. Okay, and then we're going to pick this back up on Thursday. We'll finish off we'll finish off chapter 10 basically on Thursday. Okay, we're going to go through all chapter 10, which is basically just 3 more pages. That's about it. Okay. Okay, I'm gonna upload a sample. A 2 sample practice sheet that we're going to go over on Thursday. So I'm going to upload that to Canvas right now. So make sure that you download that. If it might be in the files on Canvas as well,
I
but
think it's already on it.
it's
I
already
printed it.
there.
Yeah, I already printed it.
Okay, it doesn't have the.
Is it say a professor at a large community college wanted to determine?
Yeah, what does the next one say?
Number 2, a
Yeah.
research study was conducted about gender difference in vaping.
Yes, perfect. Okay, great, awesome. Yeah, that is correct. Okay,
Thank you.
perfect. It should be already in the files section. So we are going to finish up chapter 10, which is only a couple more pages of this, and we're going to go through the 1, 2, 3 samples. Okay, that is the 2 sample practice. We're going to go through that on Thursday as well, and that'll take us through chapter 10. All we have left then is chapter 11, and then the next exam. So exam 3. There is no exam 4. Exam 4 is a take-home exam. Okay, it's a take-home assignment, and that's exam 4, and then the final. So yeah, we have about 5 more weeks left. I think 6, maybe 5.5. 5.5 more weeks left, and then that's about it for the semester. So we're getting kind of down to the end here.
Professor, what do you mean that it's a take-home exam?
It's a take-home. It's exactly what it is. Okay, so it's a take-home exam, which means that it's for you to work on at your own pace, and then it will be due on, let me look up the due date here. It will be due on May 28th. So
Okay.
a month from today.
Okay.
So, and it's just called, and I believe this file is already up there. It's called Chapter 12 Project. And so the Chapter 12, it should say Chapter 12 Take-Home Project or Take-Home Exam or something like that. If it's not, I'll load it. But again, until we get into Chapter 12, it's something that you're going to have to use a pencil and a ruler on, and then you're going to need to scan it or take a picture of it. Now, if you do scan it and take a picture of it, that I'm only accepting PDFs for that one assignment. Okay, so you're going to need to download an app on your phone that can turn something into a PDF or something like that. Okay, it needs to be PDF and it needs to be in sequential order. But again, I'll talk more about this as it gets closer. We're still about a month away from that. So does that kind of answer the question?
Yes, thank
It's
you.
just a 4-page take-home project that I would normally give out, maybe a couple weeks before it was due in class, if we were still meeting in class. But here I'm just going to upload it to Canvas, and then it'll be due. You'll turn it in. You'll email it to me as a PDF file in sequential order. So again, if you want to scan it in order, or if you want to take pictures in order, just make sure that it's convertible to a PDF. Okay. Okay, I will be sticking around for about 40 more minutes to take questions on homework. If you have no homework questions, at this point you are free to go. So yeah.
Could you do the example from the notes right now from number 4 by hand?
For number 4?
Yeah, the one
for
that's college student.
Oh, for the college students? Example 4, let's see. Well, example 4 was the vanilla one. So which one are you talking about?
The college one where there's college A and college B, and you want to see if college B is, I think, bigger.
So that one we're finding a confidence interval?
Yeah.
Okay, so that was example 2, or example 1. This one here, I guess.
Yeah.
Okay, so there's a couple different ways to do it by hand. One's a lot more tedious than the other. So yeah, I can try to do that for you here. Okay, let me scroll down to the end here. I got some space. There we go. Okay, so yeah, let's go over this one. So we want I'm only going to go through the computation part of it. Okay,
All right.
So we're going to have x sub a is equal to n times p hat, which is equal to 240. Okay, x sub b is equal to n times p hat for b, which is equal to 418. 418.75. Okay, where n was equal to 500, p hat was equal to the 0.48, and this was 625 times the point, what was it, 67. That equals about 419. Okay, the x values have to be in terms of whole numbers. Okay, so here we're going to get p hat b minus p hat a plus or minus, okay, z star times the standard error, right? The standard error here. Okay. So what is the standard error for this? Well, the standard error is going to be, okay, p b times qb over nb plus PA QA over NA. Okay, and all these would have hats because they're samples. Okay, so P hat B minus P hat A. Okay, well, what's P hat B? Well, it's 0.67 minus 0.48 plus or minus Z star. Okay, so Z star will be, we'll get to that in a minute. It depends on what I want my confidence interval to be. Okay. I used 95% in the example or in the computation we did before. So I'm just going to say that this is 95%, which is 1.96. Okay, remember 95% is about 2 standard deviations away from the mean. Right? So 1, 2, 1, 2. This is about 95%. Okay, so this is negative 1.96 and this is 1.96. Okay, times the square root. PB, well, what's PB? PB is 0.67 times, okay, QB. Well, what's QB? QB would be 0.33 all over NB. Okay, so what's NB? NB would be 625 plus PA, that's 0.48 times QA, which is 0.52 all over all over 500. Okay, so I'm going to get this guy first, what's under the square root first. I'm going to go square root of, I'm going to put parentheses, okay, maybe a couple parentheses. Okay, now I don't need to. 0.67, okay, times, nope, don't want to close the parentheses, times 0.33 divided by 625, okay, nope, I want it underneath, plus, okay, 0.48 times 0.52 divided by 500. Okay, that should be good. That gives me 0.0292. 0.0292. Okay, that's an estimate. And then 1.96, and we will go plus or minus. Now I'm going to multiply this by 1.96 times 1.96. Okay, is 0.0572, I'll say 4. Okay, 0.05724. Now this I want 0.67 minus 0.48. 0.67 minus 0.48 is 0.19. So I'm going to add and subtract, okay, 0.05724 from 0.19. So I'm going to take 0.19, I'm going to add this answer that I got before. And I get my upper, which is 0.24, okay, 0.247, okay, 0.247, we'll say 2. Okay, that's my upper. Now if I do 0.19 minus my lower, okay, I get minus the lower here, is 0.1328, I'll say, 0.1328, okay, which is approximately what we got before. Okay, it's really close. It's not going to be exact because the calculator does a different computation than this. That gets it more exact. It gets it a lot closer. It doesn't take 1.96. It takes something closer than that. It takes this value here. I can show you what the value is that it takes. But it's just by rounding error that we didn't get exactly what we got before. What we got before was 0.133 and 0.248, I believe. And again, it's just by rounding error. What that value 1.96 really should be is this guy here. So I'm going to go inverse norm on the area, which is the area is 0.025, I believe. Yeah, and it's this value here, which is negative, which is 1.95996. So it's very close, but there is some rounding error involved. Okay?
Okay, thank you.
Yeah, absolutely. Okay, other questions at this point? Okay, let me know.